I'd like to just thank the organisers for the invite. It's quite a privilege to come and speak and highlight some of the work that we're doing in my research group. So that was a big topic that I was introduced to give. So I'm going to kind of scale it down to some work that we've been doing as more recently as part of my Rutherford fellowships. So we're going to be focusing on noise and the potential effects that this has on the marine soundscape. So I always like to start my talks with this slide. So Jacques Cousteau, the famous marine explorer, right? His famous video, The Silent World. But as I learned 18 years ago when I started this endeavour with my PhD, if you take the time to listen, it is not so silent. So we've got some soundscapes here. So the first one that I'm going to play is actually taken from Goat Island, which Tom has been talking quite a bit about. So this is off a reef out the back of the actual island. So it basically sounds like bacon frying in a pan, and there's when I first heard that, Andrew and John Montgomery, my PhD mentors, first played that to me. That's where I really got hooked. I was like, wow, I'd spent a lot of time in the water diving, and with the bubble noise, I've never really taken the time to actually listen. So this next example is some work that we did up on the Great Barrier Reef, and it sounds completely different, right? It's not so much of a pan frying, but there's more pops, and this is mainly due to the fish that inhabit different areas. So what are the sources of these sounds? So we've got three main sources. The science term is geophony, and that's the abiotic sort of sources. So the physical sources like waves breaking on the coast, wind moving across the ocean. We've even picked up earthquakes in the Gulf that have occurred out the back of the Kermadec. So it's the physical sources. The next group is the biophony. So this is the animals themselves. I'll go a little bit more into this soon. But we've got the whales, the dolphins, and some work that we've been doing on crabs. And we've got a multitude of fish that produce sound that contribute to that soundscape. And then we've got anthropophony, which is the man-made sources, and that's your shipping. We all know major shipping channel coming into the ports here. There's been the TTR proposal of Taranaki that's just now being squashed. There's all these man-made activities generate a lot of sound, and the sound is much, depending on how close you are to the activity, it's typically much louder than what the sounds that the animals or the geophony are actually producing. So noise. In my world, noise is the global warming, climate change effects. We all know, well, the world is getting louder, and probably the most comprehensive study in the terrestrial environment is the Yellowstone Park, where the snowmobiles have caused a remarkable change in the overall soundscape in that park. And it's having quite remarkable effects on the animals that live there, the moose, the wolves, and a lot of the native species that live there. So underwater, we've got a lot of different activities that are generating noise. We got oil and gas industry, even tourism, boats going out to look at whales, the sounds of the boats, shipping, and this last bottom left is marine exploration, so looking for oil and gas in the seabed to mine. And as a noise researcher or a soundscape ecologist, I'm quite lucky that I have the Hauraki Gulf at my doorstep. In terms of the noise world, the Gulf is pretty pristine, but yet we still have that little bit of anthropogenic activity. When you look at other places around the world, like this ports of Singapore, going into Singapore, the Straits of Malacca, going into Boston Harbour, going into LA Harbour, the area is really loud, and the actual soundscape that you're listening to is not what it used to be before these activities taking place. So why are we interested in noise? So this graph is part of my, picture is part of my PhD. There are a lot of animals that rely on making sound or listening to the reef or listening underwater for key life history strategies. So this example here is the life cycle of a reef fish. We got our Nemo. Typically these guys, as Tom said, they produce eggs. These eggs and the larvae are released into the water column, and then they have to find their way back to the reef. And to do that, we've shown that sound plays a key role in that navigation of getting these animals back to the reef. Sound is a good cue in that respect. It travels much further underwater than what it does in air. We're talking about 5 times further underwater, and it can carry important information about that habitat. If you listen to those 2 recordings at the start, 2 different habitats, 2 totally different soundscapes. So there's information in that soundscape that can help direct the fish back to adult settlement grounds, and then they recruit into the adult phase. This is a video. These are black angelfish. This was done out at the Mokahinas. If you look at, there's a yellow hue on the rock here. That's the eggs of the black angelfish. And you'll see, when I play the video, you'll see the male is guarding the nest, and this guy is using sound to chase away any potential conflict that he might think that could disturb his nest. So here's our male fish. And there was another one that come out here, and he chased it away. And when he's doing that, he's actually producing a sound. It's quite hard to hear. There's that kind of click sound. Next up, if we've all been fishing and we've caught John Dory or a gurnard, brought them onto the boat, and they start to make sound. I personally like to tell my fishermen mates that it's a plea for them to be put back in the water. But in reality, it's going to provide a key life history trait or promote a behaviour. With a lot of these fish, if they're not making the sound when they're doing the actual behaviour, the behaviour is not likely to be successful. So it's a commensurate thing where you need the sound and the behaviour for the act to be successful. With the John Dory, we're not actually sure what that is at the moment, but for those who haven't heard them before, basically bark like a dog. And our thoughts are that this is, it could be a mating thing that it could synchronise egg and sperm release to coincide between the male and the females. With the gurnard, we know a little bit more. We had a PhD student working on this. This first sound, so this is a grunt, and this is an agonistic reaction. So when these guys are around food and a potential predator, or well, not a predator, or a competitor comes in to try and steal the food, these guys will produce this sound, and they'll chase that competitor away. And this one is a growl, so it's a little bit different. The one before, the grunt, is the one that you hear when you pull them up. The growl is something different, and we're not actually really sure what this one is used for. We may think it's a different type. It might be a dominance thing, because typically when we've recorded these guys in tanks, they're typically produced by the large males, and it's typically produced with smaller males as well. So into the invertebrates, this is the work that I'm most excited about at the moment in terms of the animals that we're finding out that make sound. This first lot of work was done by a master's student, and when we dig into the literature, there's not actually that that much known about invertebrates making noise, and certainly not crabs and lobsters, as we'll see here in a minute. So this first one is paddle crab. So this is a zip, and basically how it produces that sound is the first walking leg brings it over top of the claw, and the claw has ridges on it, and it's basically just rubbing that claw. And this is typically produced by when these guys mate, the male holds a female, and if there's a potential competing male, it's that competing male produces that zip sound to try and get the female away from the male that's holding it. And this is what we've termed the rasp. And this is produced in a feeding context. So if you drop food into a tank, we get a whole lot of rasp, and we think that's a communication thing between other animals, other crabs in the tank, to let them know there's food around. And we get the same sort of thing with the lobster. It's just a different type, different frequency response of the rasp. Did that one play? So it's very short, much more high pitched than what the crab was. And then we all know about the mammals. I won't go into all the mammals that we've recorded, but this one is the Brooder's whale, and we've recorded a few of these animals out in the Gulf. And you have to listen really careful to this. It's quite low frequency, and there should be 3 burps, if you like, with the last one being the loudest. So we know that many more fish in the Gulf are making sound. We have hours and hours of recordings, and there's a lot of unidentified sounds that we know. So when we're recording these, it's basically a process of elimination. We look at the sound, we compare it to what we know, and if it doesn't compare, then it's obviously some other type of animal. This is my favourite. This is a big eye fish. These, if you like, are my model organism. We've done a lot of work on them, and they produce this popping sound. So these guys typically hide out in the caves during the day, and they come out at night to feed in the plankton. And we know a lot about these guys. We know what their sound is. We know how well they hear. We've done some physiology on that. And we also know what the behaviour, what the sound is used for, what behaviour context is produced in. So they produce a contact call, and this is the first evidence, hard evidence, that is being provided in a fish species. If you think about contact calls, it's normally large mammals. You got your elephants produce real low infrasound to maintain the structure of their herd. And a lot of the marine mammals produced contact calls to maintain the structure of their pods. So what is a contact call? So it's a sound that's produced to tell the nearest neighbour around them basically how far away they are, and to maintain what's happening. So we got 2 scenarios. So if the ambient soundscape is loud, the fish are going to be closer together. If it's quiet, they're going to spread apart. So if they're out feeding and a boat comes by, they're going to school up and become closer together, which is going to affect the way they feed, because they don't have access to as much plankton to what happens if it's quieter and they can be further apart. So this is the first graph. I've only got one other graph to show. I didn't want to show too many plots like this. But just to orientate you with it, we got frequency in hertz on the x-axis, and we've got sound level, or how loud the sound is, on the y-axis. And each one of those lines represents a different animal that we've recorded in the Gulf. So now going back to our How long have I got? Okay. Going back to our noise issue, if a boat come by, what would theoretically happen to that soundscape? It would basically just blank it out. Boats, depending on different types of boats, they're pretty broad frequency and they're typically really loud. This is a recording of a ship coming past one of our hydrophones, so it's about 500 metres away. So basically it's just the sound of the props and the engines. And if we were to look at that on a loudness scale, underwater, that would relate to a train going past in a New York or London subway. So the equivalent underwater, it is really loud. So what do these potential effects have on the animals? In this diagram, if we think of the fish in the middle, if we're going to the left, we've got decreasing source level, so the sound's getting quieter. If we go to the right, it's the animal getting further away. So in the middle, really close to the source, where it's the most intense, there's potential for actual injury to the animal. So there's been research showing that swim bladders have burst, livers bleeding, and there's quite a lot of internal damage. As we move away, we got PTS, which is a permanent hearing threshold shift, so the animal's hearing ability is changing. We got TTS, which is a temporary shift, so the animal's frequency bandwidth, hearing bandwidth's changing by a little bit, but comes back a few hours later. Then we've got the last two, which is where I'm working on, and that's masking. So that noise by the ship is masking that sound to be heard from the emitter's target. And then they can change behaviour. With a lot of the fish, with a lot of research that's gone on, is that they're holding fish in tanks. But in reality, what I think is if the fish is going to hear a loud noise, it's not going to hang around and suscept itself to being hurt. It's liable just to swim off. So in terms of masking, we've done some modelling. So this is the other graph I'm going to show. So this top figure is basically AIS data of some ships coming into ports of Auckland. This is done out just in Jellicoe Channel. And these lines represent a ship and how close it comes to our hydrophone, our listening station. So this is a 24-hour period. In this period, we had, five or six ships come within a 10-kilometre radius of our hydrophone. And that bottom picture is what is actually happening to the soundscape in our bins. So you can see we got time on the X, frequency on the Y, and the colour represents the intensity level or how loud that ship is. So every time the ship comes past, it increases the ambient or the background soundscape. What does that have in terms of effects? Well, that's our ship. So this is where the star happens. This is how loud that ship was. What is that happening to our animals? So we use two animals in this modelling. We use the Bryde's whales and the big eye fish. We know what the sound is that's produced by the Bryde's whales. We know a whole lot more about the big eye. And based on that, we can actually work out the communication space of that animal. So the distances that these animals can potentially communicate over in an ambient where there's no artificial or man-made noise happening. So Bryde's whales can... sorry, lost my thought. The Bryde's whales can communicate over a much larger space than what the big eye fish do. That's because their sound's much louder than the big eye. When we get the vessel coming past, the middle part of the diagram, and we can calculate what that effect has on reducing that communication space. And the end numbers come out to about, it reduces that space by up to 99.9%. So the effect that ships have on an animal that's communicating in the ocean is quite large, because it basically the cocktail effect, right? If you're at a party and you're trying to listen to your mate, you have to be a lot closer if it's really loud than what it is if it's a dull party and quiet. So the same thing is happening with these animals. When they're trying to talk to each other and communicate, if a loud human-induced activity is affecting their ambient environment, they have to come much closer together to communicate. So just some take-home messages. And firstly, sound plays a critical role in the life history studies of many marine animals. We're talking vertebrates, the fish and the mammals, and also invertebrates. This is even becoming more important given that there's many more invertebrates than vertebrates in the marine environment, and every couple of months there's a paper coming back out of a new species actually making sound. The world's oceans are getting noisier. We're increasing shipping's efficient way to transport goods around the world. Commercial ships are getting bigger, and there are more of them, so the actual ambient soundscape is getting louder. So we really need to understand, go back to the basics. We need to understand what animals are making noise, what the noise is actually used for, how sensitive are they to that noise, because that'll play a big factor in the effects of the anthropogenic activity, and how that anthropogenic activity is going to disturb that behaviour. The one good thing about noise compared to, say, ocean acidification is that if you actually remove the source, it solves all the problems, right? It's gone. There's no kind of waiting around for the pH to equilibrate like there is with climate change. And a lot of this work wouldn't have been done without my colleagues and collaborators and students and funding, so I'd like to acknowledge them as well. Thank you.